This is episode 3.1 of the GWM tutorial series, and we'll be looking here at additional GWM features, in particular summation constraints, the SUMCON file. We'll look at an example that has both injection wells and withdrawal wells, and it has multi-cell wells. In addition, it has head difference and head gradient constraints, and that example is the seawater example problem. Here we are in the distribution directory for GWM 2005, version 1-5-2, and if we look in the doc directory, we see this file, which is a USGS open file report, which is one of the first reports, or the first report for GWM. Turning to page 68 of that report, we find this figure, which is a depiction of the grid for the seawater problem. This is a two-layer problem. The top layer is modeled as unconfined and the lower as confined. Recharge is applied over the domain to reduce the flow from left to right. The sea, the ocean, is modeled as being along this boundary with a constant head of 0 feet. There is an existing production well in the model, which is screened over two layers. This well is modeled, by the way, in the well package of ModFlow and will be represented without modification in GWM. This is a steady state problem, and the management issue here is one of saltwater intrusion. It is desired to install some additional withdrawal wells at one of the 5 locations, or one or more of the 5 locations, while ensuring that there is no significant saltwater intrusion. Saltwater intrusion is monitored by imposing constraints on head differences along the sea boundary, and can be controlled by the use of injection wells. The overall objective is to maximize the net withdrawal of water, that is the withdrawal from the 5 wells, minus the injection needed to control saltwater intrusion. The system is modeled as a single phase, just the fresh water, and the salt water is represented through the boundary conditions. This now a cross section of the 2 layers. So in column 30 there are specified head conditions in the both layers, and also in column 29 in the second layer, thus representing the saltwater wedge. Horizontal gradient constraints, head difference constraints, will be used to force a gradient, and also vertical head difference constraints will be used. Note that some of the candidate wells are screened over multiple layers. So let's now turn to how this problem is set up in GWM. Back now to the distribution directory for GWM, into the data directory, and we see the seawater problem, and here we have the input files for that problem. We'll start with the GWM file, and here we see that this file includes decvar, objective function, varcon, headcon, and a new keyword, SUMCON. And we'll cover that in just a moment. But let's look at the other files that we're now familiar with and see how some of the features of this problem are handled. And we'll start with the decvar file. So we have, in this case, 8 flow decision variables. And the first 4 of these are quite similar to those we saw in the dewater problem. Variable name, layer, row, column, withdrawal, etc. The fifth well, W5, includes a new feature. This well is screened over 2 cells, and so the number 2 is introduced in the NC variable location, and then it is understood that in that line of data the layer, row, and column are ignored, and instead GWM looks for additional information in the following lines. Specifically, for the 2 cells associated with that W5 decision variable, GWM needs the ratio, in this case 50% from each of the 2 layers, and the layer, row, and column number associated with those 2 cells. So you can see that they are in layer 1 and 2, one on top of the other. Another new feature of this problem is the use of injection wells. As the name indicates, there are 3 of them, I1, I2, I3. But GWM becomes aware that they're injection wells by the change in the F-type variable, where I is used instead of W. Once again, GWM will figure out which sign to use when performing calculations associated with these decision variables based on whether it's withdrawal or injection. These injection wells also are multi-cell and use the same format as previously described. Next, turn to the varcon file, and the only interesting thing here is that we have the 8 decision variables, and we're including, of course, the injection wells, lower and upper bounds. And here you see they're all positive numbers, regardless of the direction of flow. Next, we look at the objective function file, and here we have the 8 decision variables are all included in the objective, and the interesting feature is that the injection wells have a minus sign associated with them. So effectively, we're maximizing the withdrawal and minimizing the injection, because we'd like to make these because the negative coefficient, we'd like to make the injection values as small as possible. We'll now look at the head constraints file, and here we have 3 different types of head constraints. Head bounds, as we've seen before, and these are upper bounds on head at the injection points to avoid mounding, 3 of them. And then we have 10 head difference constraints, and those are listed here, and they consist of an indication of the 2 cells involved in the head difference and the magnitude of the head difference, in this case 0.05 feet. And then finally we have 20 gradient constraints, and these once again indicate the cells over which the gradient will be computed, the distance over which the gradient will be computed, and then the bound on the gradient. And the requirement is that the gradient from the first cell to the second cell be greater than the value indicated. Returning to the report, we see the objective function maximize the sum of the withdrawals minus the sum of the injections, and we also see an explicit constraint placed on the relationship between the total withdrawals and the total injection. Specifically, we'll want to make sure that we are not that we are withdrawing more water than we're injecting. So this is going to be an explicit constraint. How is this introduced into GWM? This is done using the SUMCON package in GWM, which allows the introduction of any linear combination of decision variables or state variables as a constraint. And we do that, we input that through the SUMCON file, and here it is for this particular problem. The first thing we've done is rearrange the equation by moving the injection wells to the left side of the inequality so that we have the sum of withdrawals minus the sum of injections is greater than or equal to 0. And that's the form we will use in the summation constraint. So in order to define the summation constraint, we need to specify the direction of the relationship, in this case an inequality, and the right-hand side, and the coefficients on each of the decision variables that will be in the summation constraint. So the way this works for this particular file, we have one constraint, and we have some information about that constraint. We have its name for the summation constraint. We have the number of terms, 8 in this case. We have the direction of the constraint. It could be an equality or less than or equal to, greater than or equal to. We have the right-hand side, which is 0, and then we have the list of variables that are in the summation constraint and their respective coefficients. Now take a quick look at the output file for this problem, and we see the 8 decision variables, 5 withdrawals and 3 injections, applied over multiple cells in some cases. We see the objective function maximize the combination of withdrawal and injection wells. Variable constraints, we see the summation constraints, constraint name, and the constraint statement with the coefficients, the variables, and the right-hand side. We then see the head constraints, 3 different types. And then the solution file and on to the solution. You'll note in this case that initially all constraints are satisfied under the non-pumping condition. This is a nonlinear problem, and the algorithm used is the SLP algorithm, which will be discussed in a later episode. Here is the ultimate optimal solution. We have quite a bit of withdrawal, a little bit of injection, and we can see where the constraints are binding, which locations produced binding constraints.